Today the topic of our discussion is probability and distribution. So in this session we will explain basic probability concepts and rules, understand conditional probability and Bayes theorem, describe binomial, Poisson and normal distribution, explain the central limit theorem and apply these probability models to health data problems. Now coming to our introduction section, what is probability? Probability is the likelihood of something to happen. Like if we have a dice and there are 6 sides, so what is the probability, what is the likelihood of one side to happen? So it is always expressed as a number between 0 and 1. 0 means it cannot happen. It is the event is impossible, and 1 means that the event will definitely happen. So we often convert probability into percentages for easier understanding. A probability of 0.5 means there is a 50% chance that it will happen. So for example, imagine we roll a dice which have 6 sided. What is the chance of one side to occur? So the chance of getting a 6 is 1 out of 6 or 1 by 6. So the probability will be 0.167, which is about 16.7%. Now let's learn what is sample space and events. So what is the sample space? Sample space is all possible outcomes. For example, if we have a coin, so the sample space will be head and tails both. If we have done a pregnancy test, so what will be the sample space? The sample space will be positive and negative. Now coming to event, the event is always a subset of sample space. It is just one outcome of a sample space. For example, from the coin example, the event may be head or may be tail, and from the pregnancy test, the event may be positive or negative. So these are sample space and events. Now coming to conditional probability, what is conditional probability? So the conditional probability is if we already know B, then what is the probability of A to happen? This is a very most important in health because we often want to know the chance of a disease given a certain condition or test results. For example, if we have a positive test, then what is the probability that the person with positive test has the disease? Like we have two events A. What is A? A is the patient really has TB, and B is the test is positive. So what will be the conditional probability? Among all patients who is tested positive, like the B, what is the proportional of patient actually having TB in B? So coming to our example, let's imagine we have 1000 patients. Okay, so our prevalence for TB is 10%, so there will be 100 patients of TB. Sensitivity is 90%, so the test will give positive results for 90% of patients, which will be 900. Test specificity is 80%. Now let's calculate the conditional probability. Okay, what will be the true positive? True positive is 100 are the actual positive with TB patients, and our sensitivity is 90%. So if we multiply these and get the value, there will be 90 patients which will be true positive. Now coming to false positive, if okay, Now there are 900 non-TB patients. 100 are TB patient and 900 are non-TB patient. So what will be the false positive? So the false positive here 80% is specificity, which means it will correctly give negative values 80%. So the 20% it will give false positive. It will be not positive. It will be positive, but it will be not TB patients. So if we get the result, it will be 180. Now the total positive will be 90 plus 180 270. And the actual positive is 100 and true positive is 90. So now we know that the positive results are 270 and the true positive are 90. So the probability is 0.33. It means that only 1 in 3 patients with positive test results actually has TB. Now independence means that one event has no influence on the other event. Like if one event is happening, so the other event has no influence on changing the probability of the first event. In other words, knowing that one event has happened does not change the probability of other event happening. Like if we flip a coin and for example the heads occur. So if we flip the coin second time, it will not change, it will not influence the second event. It may be heads or tail, but it cannot influence the second event. For example, okay. Now we have tossed a coin twice. Probability of heads is 50%. Probability of head for the second toss is also 50%. So this is the independence. It is not the first event has not changed the second event outcome. So the probability of getting heads on both tosses will be the multiplication rule will be applied and it will be 25%. Now coming to Bayes theorem, what is Bayes theorem? Bayes theorem is a tool we use when we want to revise our belief about an event after we get new information. In medicine, this is extremely important because we often have some idea about how common a disease is, and then we get new information like a test results. Like we get the information about test results, and then we revise our belief about the probability of the disease. So if we start with probability of A, the prior probability, then we get a new information on the test, like to get probability of A knowing B. Okay, now this is our new belief. For example, this is a test, prevalence is 1%, sensitivity is 99%, specificity is 95%. So in the specificity, the disease is negative and the test is also negative. In the sensitivity, the disease is positive, and here there is an HIV. Okay, let's apply this theorem. Now the formula for this theorem is probability of a disease, probability of a test if we know the disease, then probability of the disease, and then similarly this will come here plus probability of the test with no HIV, and this is the probability of no HIV. Okay, so here the sensitivity is 0.99% the probability, because the sensitivity gives us positive results. Okay, so the probability of HIV will be 0.01. So prevalence is here. Similarly for this and for this, it is actually The positive results, like this is the negative results with HIV, there is no HIV, but we need positive results with no HIV. So it will be subtracted from the specificity and it will come 0.05. Okay, and then the probability will be from the sensitivity 0.09 here, and it will give us the results like the probability will be 0.166. It means that if the test is very sensitive and fairly specific, the probability the patient truly has HIV after a positive result is only 16.6%. Now coming to probability rules, here are three rules in probability: addition, multiplication, and complement. So in the addition rule, if we add the probability of two events, then the formula will be probability of having a cold and probability of having a fever. It is 0.3 and 0.2. But if there is an overlap, we will minus it from these two. So the probability will come as 0.4. Now it shows us that 40% chance of having cold or probability or a fever. For example, if there is 0.3% chance of cold and 0.2% chance of fever, then what is the probability that it will be either cold or fever? The addition rule is applied for this. Now the multiplication rule, this rule shows us that both the event happen simultaneously. So the probability of A multiplied by probability of B. If we have smokers, the probability of 0.3%, and if probability of having lung disease given smoker is equal to 0.2, then if we multiply these, then it will give us the results that the patient is a smoker and also has a lung disease. So 6% chance that a randomly chosen person in both a smoker and has a lung disease. There is a difference in addition and multiplication rule. In multiplication rule, the last probability shows us both the results in same patients. But this probability shows us that the collective probability will give us either cold or fever. It will not give these two, cold and fever, in same patient. In complement rule, if the probability of A is known, then the probability of not A is 1 minus probability of A. For example, the probability of patient surviving is 0.9. So what will be the probability of death? So it will be 0.1. So coming to distribution, discrete and continuous distribution. A discrete distribution is used when the possible outcomes are countable and separate, like the values will be whole numbers. Probability for all possible outcomes add up to 1. Like we have discussed previously, it will be 0 or 1. So the probability of all possible outcomes, if the outcomes are 2, the probability of all the outcomes will be 1. If the outcomes are 4, again it will be 1. You cannot get fractions between those numbers. In the discrete distribution, we cannot get fractions like 0.1, 0.3. It will be always in whole number. From data, count how often each outcome happens and divide by total observations. So this is the example, the number of patients visiting a clinic. Possible outcome is 0, 1, 2, 3. You might get 0 patient or might get 1, 2, 3 and so on. But you cannot get 3.5 patients a day. because if we don't have half a patient will always be one. So the discrete distribution help us calculate the chance of getting each possible count of outcome. For example, the probability that exact 4 people test positive out of 10. So in the discrete distribution, if we add all the probabilities of the patient, how much patient coming each day, so the total result of probability will be 1. Binomial distribution. Model situations with 2 possible outcomes per trial. For example, success or failure, positive or negative, in the kind heads or tails. These are binomial distribution. Example in health, success is patient recovers and failure is patient does not. Success is the test is positive and failure is test is negative. Key feature, X number of trials. Each trial will be independent. Probability of success is constant. For example, probability that exactly 3 out of 5 patients respond to a drug. Now there is Poisson distribution. What is it? Models the numbers of events happening in a fixed time or space when events are rare and independent. For example, number of new COVID-19 cases reported in a day and number of hospital admissions due to heart attack in an hour. So what is the key features? The key features is it is defined by single parameter lambda, which is the average number of events. In short, binomial and Poisson shows us that in binomial the outcomes will be yes or no repeated a fixed number of times. In Poisson, count of events over time and space, especially when events are rare. It is used for the rare events and which are over time and space. Now this is a continuous distribution. A continuous distribution is used when a variable can take any value within a range. Like it can take a value from 0 to 10. It may be 9.5, 8.5, 8.1. Unlike discrete distribution, continuous variables are measured, not counted. Patient blood pressure can be 120.0, 120.5, 121.3, any value in a range, and the weight can be 60.2, 60.25, and so on. So the most common example of the continuous distribution is normal distribution. It is a bell-shaped which is symmetric. Most observations are near the mean and fewer are very high and very low. The key idea is that the continuous distributions help us calculate the probability that a value falls within a range. Probability that a newborn weight is between 2.5 kg and 3.5. So what are the rules for the normal distribution? 68% of values lie within one standard deviation. 95% lies within 2 and 99.7% lies within 3 standard deviation. And the health example is height, BMI and blood pressure. It can be measured in decibels or within a range of values. Now z-score, what is z-score? A z-score tells us how far a value is from the mean measured in standard deviation. It helps compare values on a standard scale even if they come from different distributions. Like the z-score measures the value in standard deviation, but it shows us that how much the value is far from mean. The x here is observed value and the second is mean, and the third is standard deviation. This is the formula for z score. Now the interpretation is, if z is equal to 0, then the value is exactly at the mean, and if the z is greater than 0, then the value is above the mean, and vice versa. If the z is less than 0, it means that the value is below the mean. For example, if the blood pressure is 150 and the mean is 120, standard deviation is 15, and the z value is 2. As it is above the 0, it is greater than 0, it shows us that the value of blood pressure is above the mean, which is 120. Now, central limit theorem. But what is central limit theorem? If we take many random samples from any population and then calculate their means, okay, we take many samples from a population and we calculate their means. This is the first step, calculation of the means of many samples. Then the second thing is the distribution of those means. If we distributed these means of different samples on a graph, it will get closer and closer to normal distribution. This happens even if the original data is not normal, as long as the sample size is large. Why the central limit theorem matters? Because it uses the normal distribution to make conclusion about population, build confidence intervals, and do hypothesis testing. For example, suppose we measure cholesterol levels of 30 random patients, calculate the mean. We will calculate the mean of 30 random patients repeatedly. Like there is a population, we will get a sample of 30 patients and calculate a mean. Then we will get another sample of 30 patients and we will calculate the mean, and so on. If we do this for many samples and calculate the mean, then we will distribute the sample means which is calculated from different samples. These mean will give us a normal distribution. Okay, now let's coming to the practical applications of probability. Probability is at the heart of medical test interpretation. The first is diagnostic test accuracy. So the probability is used in the key measures are sensitivity, specificity, positive predictive value, and negative predictive value. In sensitivity, the probability test is positive when disease is present. For example, the sensitivity gives us only the positive tests, but how much of the positive tests actually has the disease, which is the work of probability. The probability will tell us that how much of the positive test is positive. Similarly, for specificity, the probability will tell us that how much in negative is actually negative. And then there is a positive predictive value. The probability is used in it. Probability patient truly has disease if the test is positive. Similarly for negative predictive value. For example, if a disease is common, positive predictive value increases. If disease is rare, then many positive results may be false positive. Example, suppose HIV prevalence increases in a population. So the same test will be applied, more true positive will appear, probability that a positive result is real. For example, because the prevalence is high and the test gives us more positive, so the probability is that there will be more patients and more true positive. Now, the use of probability in risk calculation. Risk calculation in health research is simply applying conditional probability to disease occurrence. What is the key idea? We often want to know what is the probability that someone will get the disease if they are exposed to a risk factor. For example, in cohort study, if someone is exposed to certain risk factor, what is the probability of having a disease? It can be used in cohort study, follow exposed and unexposed group over time to measure risk, and then in risk assessment, estimate how dangerous an exposure is, like radiation, air pollution, smoking, unhealthy diet. Now this is the example for risk calculation. In a study of smoker and lung cancer, the exposed group and unexposed group. In exposed group, there is 30 out of 100 developed cancer, and in non-smokers, 5 out of 100 developed smokers. So the risk in exposed is 30%, and the risk is non-exposed is 50%. So what will be the relative risk? The relative risk will be probability of disease and exposure divided by probability of disease with no exposure. So the smokers having 6 times more likely to develop a lung cancer. Now application in outbreak modeling. Poisson distribution is very useful in modeling outbreak. We have earlier discussed this, that events in time and space and rare events is used in Poisson distribution. So it is useful in modeling outbreaks because it predicts how many events will occur in a fixed time or place. In a fixed time or space. Key idea. Outbreak often involve counting cases per day or per week. When events are rare and occur independently, Poisson distribution gives a good estimate of probabilities. We have discussed it earlier. For example, if the community averages 3 new measles cases per day, the Poisson distribution can calculate probability of exactly 0, 1, 2, and so on with time or days. For example, one day we have 3 measles cases, the next day we have 2, the third day we have 5, the fourth day we have 4. So there is a time like first day, second day, third day, fourth day, and there is a space or place in which we will measure the measles cases. Why is it useful? Resource planning, forecasting, and decision making. For resource planning, predict hospital bed needs and medicine stock for the measles. Forecasting, know when to expect peaks or when outbreak is ending. Like we are forecasting, we are planning for the disease or an outbreak to occur. And decision making helps public health authority prepare for possible case search. Now the application in reference ranges. In medicine, we often need to decide whether a test result is normal or abnormal. This is done using reference ranging, which are usually based on the normal distribution. The key idea is in a normal curve, about 95% of values lies within 2 standard deviation. This interval is taken as a reference range, the 2 standard deviation. Then values outside this range are considered unusual and may suggest disease. For example, suppose a mean fasting glucose is 90 with standard deviation of 10. The reference range is 90 plus minus 2 into 10. So it will be like the 2 is from the 95% area of a normal distribution and 10 is the standard deviation. So we will have reference range of 70 to 110 mg per dl of fasting glucose within 2 standard deviation. A test result of 120 falls outside. If a value increase from 110, then it will fall outside the 2 standard deviation into 3 and so on. Why it is useful? It helps doctor quickly see if a lab result is within normal variation. For example, the fasting glucose is uh, correct up to 120, 115, and the random blood sugar is normal up to 170. Identify patients who may need further investigations or treatment. Widely used for blood test, blood pressure, and cholesterol. So this is our topic, the probability which is used in health. So these are some practical questions. You can see it and solve it later. And this is the summary. So probability quantifies uncertainty and certainty. The key rules are addition, multiplication, and complement. The distribution are binomial, Poisson, normal are discrete and continuous. So the normal distribution is the continuous distribution, binomial and Poisson is discrete distribution. Central limit theorem explains why normal is widely used. This is about the means of samples and application in health, like in the diagnostic, risk estimation, outbreak modeling, and reference ranges. Thank you for watching this lecture.